Morning, class. Whoa, good haircut. A little difference, right? It's more noticeable when you... I like it. Well, I hope you guys had a good weekend. I got test results back this morning. So they're posted on WebAssign. You guys are consistent anyway. You know, the average always falls in the C range, where average is what it's supposed to mean. There were, I'm trying to remember, about 10 A's, 10, 15 B's, 10-ish C's, can't remember how many D's, 11 F's. The highest was 29 out of 30, and the lowest was an 8. So there you go. If you didn't notice, the retake is still open because our test was on Friday. So normally you've had 4 days. So it's still open until tomorrow. Thus, it didn't close Sunday night if you choose to retake it. Retake meaning you were here and you're allowed to retake it because you took it the first time. Well, we're going to start a new unit, last unit. And my original intent was to be chapters 26, 27, 28, and 29. We'll definitely do the first 3. I'm still debating on the last one. I didn't realize how much material he crammed into 28, so it might take us longer. Or we'll just slow down and ease up and test you on less. I'm sure you wouldn't cry over that, would you? We'll see how it goes when we get to 28. But my favorites are this week, light and color. That's what your first set of homework will be due on 26 and 27. So even if I start 28, your next homework's only on 26 and 27, and it's due Sunday. And then we'll worry about 28 and maybe 29. Do you guys have any questions or concerns about anything? Comments, revelations, neat things in nature you observed over the weekend? That's okay. Thought I'd ask. All right. Chapter 26 is on the electromagnetic properties of light. So that's where we're going to start today. Light is my all-time favorite subject. I love it. So we'll discuss some of the properties and how it interacts with matter on chapter 26. In 27, it's about color. Yeah, who doesn't like color? And how things appear and why they appear that way. Chapter 28 is how light behaves. And believe it or not, you guys already know most of that stuff because light acts like a wave. And we've discussed waves and sound and how they interact. Interference, reflection, refraction, bending, all that happens to light. 29 is the wave nature of light specifically. And we'll see how far we get through that. So, to begin with, let's turn on the screen. And I showed you this when I was talking about a transverse wave. I'll show you again so you guys can better visualize what light looks like. So, light, and from now on when I say light, I'm going to mean the whole electromagnetic spectrum, electromagnetic radiation. Visible light is just one small part of that, and I'll show a graph of that in a second. But all forms of electromagnetic radiation, light, travels like this. It doesn't need a medium, and it's transverse. You can see that this, pick a yellow column, it goes up and increases and then decreases. Goes negative, increases, goes to 0, increases positive, back to 0, decreases negative. So it's vibrating, but the wave propagates perpendicular to that. We could say the yellow here is the electric field. It's changing and variable. So the electric field increases in one direction, decreases, goes to 0 at some point, and then increases the opposite direction and back. The blue is like a magnetic field, and it's oscillating perpendicular to the electric field. What I chose not to cover this semester was the chapters we just skipped, electricity and magnetism. And the gist here is that a changing electric field can create a magnetic field. And the flip works too. A changing magnetic field can create an electric field. That's the connection between electromagnetism. And once they made that connection, they made it to light also. It was a grand day. So anyway, there you go. The source of all electromagnetic waves, what do you think it is? What's the source of all waves, period? A vibration, a wiggle. So what do you think has to wiggle to make an electromagnetic wave? Electrons. Some charge. You can charge up a rod and wiggle it back and forth, and you create an electromagnetic wave. The faster you do that, the increase in frequency. But yeah, the source is charges. What's actually waving here? You know, with sound waves, we've got the air molecules, you know, me talking. They're what's wiggling, but the wave propagates through the air. What's actually waving here? It's right up there. They're kind of waving. Looks like they're traveling at you. The electric and magnetic fields. That's all I'm getting at. So the sources are charges, usually electrons. And the wave still propagates at vibration in these electric and magnetic fields. Here's the electromagnetic spectrum. So here's the waves. They have wavelength and frequency. On this end with gamma rays, the frequency is really high. Thus the wavelength short. And on the other end, radio waves, they're really long. And they're vibrating more slowly. They all travel at the same speed though, the speed of light. 300 million meters per second. 300 million meters per second. They all travel at the same speed, but they have different frequencies and wavelengths. And the visible spectrum right here is, how do I say this, 1/1,000,000th of 1% of the whole measured electromagnetic spectrum. So the light that we can see, the visible range, is a very, 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 very small part of this whole spectrum. So again, when I say light, that refers to all these. It's just most forms of light are invisible to us. But they're out there, around us all the time. All your Wi-Fi gadgets, electromagnetic radiation, microwaves, radio, visible light, infrared, the heat. How many of you like glow-in-the-dark things? That's all ultraviolet. Waves can make those things vibrate. X-rays. Everybody in here has probably had an X-ray, whether you realize it or not. And how many have been on a plane flight? You get exposed to gamma rays because they're more intense the higher up you are because you're less shielded. They're everywhere. They're all around us, going through us right now. Notice, purple end, the blue end, has a shorter wavelength. It's 400 nanometers. That's 400 billionths of a meter. Nano is a billionth of a meter. And red is around 700. So red is longer wavelength. So who has the higher frequency? Got one vote for red. Two votes for red. Okay. That's the wavelength. Unfortunately, you're incorrect. This still applies. Sorry if you can't see it in the dark. Here. The wave speed is equal to the frequency times the wavelength. Here, the wave speed of light, we give it a c because it's constant. And frequency and wavelength. So if one of these is different, the other is different. Red has the longer wavelength. So the wavelength's bigger. So the frequency will be small. That's, what am I saying wrong? That did not come out right. I know blue has a higher frequency. Why did I just say that wrong? Bigger number, small. Yep, that's what I get. 400 nanometers, bigger waves, lower frequency. Oh. Yeah. We said it right. I thought, oh, that happens to me all the time. Okay. Red does have the longer wavelength. You can see that. That's right. So if this is a bigger number, this is a smaller number. If that's a smaller number, it's not vibrating as fast. That's what was throwing me off. Smaller number, I was thinking it was vibrating faster. But smaller number means it's not vibrating as fast. 50 hertz compared to a million hertz. A million hertz is vibrating faster. So, again, if wavelength goes down, frequency goes up, or vice versa. My point here is I want you to remember that red has a longer wavelength, blue has a shorter. Blue is vibrating faster, higher frequency. Red is a slower frequency. But they travel at the same speed. So when we get into color and reflection and refraction, if you know that, that'll help you. Okay. Let's send this up a little. There's less shadow on the board. So that speed of light is 300 million meters per second. You've seen that before. If you're curious, in air, it's pretty much that. In water, it slows down. In glass, it slows down even more, and diamond even more. And that's what I'm going to discuss next. You got different types of materials. What happens when light goes through them? It's kind of like our Newton's cradle from collisions. We use these as analogies. If you have a light wave coming in, then you end up with a light wave coming out. You could say this material is transparent. This light is vibrating at a certain frequency, and when it hits these, it's going to make them vibrate at the same frequency, right? It's going to try. And then this one vibrates, hits this friend, hits his neighbor, hits the end one, and it comes out because it's free to. And that's what light does when it goes into something. It has a certain frequency, and it causes the atoms and molecules and electrons in the material to start vibrating at whatever frequency the incoming light is at. Let me say something else first. This is my other example. Remember resonance? These two tuning forks are tuned the same, or pretty close. And to show you, I can still hear one really slow beat, which means they're really close. Remember the higher the beats, the farther apart they are. So again, you got an incoming wave that likes to vibrate just like a tuning fork. Your author of your text really likes the analogy of tuning forks. So if you hit this one and you send the wave into the material, we did this before, but it causes the wood to resonate at that frequency. The tuning fork naturally wants to resonate at that frequency, and so it does. It vibrates and emits its own vibration. You can think of this as an incoming light wave, and the ping pong ball is an outgoing light wave. Now, something that's interesting, if I get these off a little, let's change the mass on this so it vibrates a little differently. Yeah, hang it back up there. Can you hear the faster beat? Now they're less in tune with each other. Different frequencies. What do you expect to happen now? Do you think the ping pong ball will move?
Yeah.
Thanks. Let's see. Yes. The incoming waves don't always have to match the natural resonant frequency of the material. This is like the driving frequency, the incoming wave, and it's trying to make this wiggle. And it'll make it wiggle, but if it naturally wants to resonate at that driving frequency, we call it what? Resonance. And it'll vibrate even more. And this will help us determine whether objects are transparent or opaque. If you drive it at its resonance frequency, this will vibrate more. And think, each of these little atoms, molecules, electrons, if this one comes in and it makes this one wiggle a lot, and this one wiggle a lot, and this one wiggle a lot, you can see if they're all wiggling, the wave doesn't transmit near as efficiently. If they're all kind of holding still, it gets kicked out. But if they're all kind of already moving, you can get something, but not as well. My crude analogy here is that if this is at resonance, they start wiggling a lot and there's more interactions, and that slows the light down. It actually absorbs the light completely, and we'd say that that object is opaque. It doesn't let light shine through it. If it's off resonance a little bit, it can still make it wiggle, but instead of all that wiggling going into internal energy, it'll bump its neighbor and can make its way out. If it goes through something, it's transparent. If instead it makes it wiggle, but it re-emits it back on itself, it reflects light. And we'd still say it's opaque, because it doesn't pass through it. Some things to note now, important points that I want you to know. The incoming light is not the same as the outcoming light of an object. So the red I see from your jacket, there's light coming onto it. Some of those atoms get vibrated by the frequencies in that light. They wiggle, hit their neighbors, re-emit their own light at the same frequency, the frequency they like to wiggle at, and it comes back at us as red. Whereas a piece of glass, I don't have like this, same thing. Light comes in on this side, makes those atoms wiggle, they hit their neighbors, they give off their own light, the neighbor absorbs it, gives off its light, its neighbor absorbs it, gives off its light, till it exits the backside, and it's transparent. But the light that comes out this side is not the same light that came in, but they are at the same frequency. That's why you still look like you. If it's opaque like this, or your jacket, the light doesn't go through, but it still comes. If the light on this is at resonance, then that light gets absorbed more. Because again, it makes it wiggle more. And you know what happens when the material inside wiggles more? There's more energy going to the material, less in the light wave. It absorbs it. And you get less light to go through or reflect. And we'll talk more about that when we get to color. That determines which colors get absorbed and which color reflects back. Color refers to frequency. That's why I wanted to emphasize red and blue up there. Just like kind of with sound, the color of a sound had to do with all the frequencies that made it up. The partials, determining its quality. The book used the term color also. I did once or twice, but we usually called it quality or timbre. Color is similar. Does that make sense? I hope so. So it's not the same light that comes in that comes out. Whether it's on resonance or not, whether it gets absorbed, and whether it reflects back or passes through, opaque or transparent. Let's give you another example here. If you have a piece of glass. Oh, I don't think I emphasized enough. Another very important point. That's why light slows down when it goes through something. It's those interactions. Because it takes time to make one wiggle, and then his friend, then his friend, then his friend, and to get through. The more interactions you have, the slower the light's going to travel through that medium. But once it exits, it goes back to its normal speed. So now to this example. What passes through glass? Visible light. So, do you think visible light, do you think the molecules and atoms and electrons in glass want to vibrate, resonate at the frequency of visible light? Yes or no? No. Yeah, it still makes them wiggle and they emit to their friends, but it exits. You don't lose it to internal energy. They don't resonate. They don't match up. But what would this light be? It's higher frequency, shorter wavelength. Do you know what we call it? What's just higher frequency than visible light? X-rays are, yeah, but there's something in between. I know I just showed you the thing, but some people are familiar with the spectrum. Ultraviolet, yeah. I'll call it UV for short, ultraviolet. Glass molecules, the electrons, do resonate in the UV frequency. So it's going to make these guys wiggle a lot and absorb the UV. The energy in this wave is going to go into the motion, the vibration, and the internal energy is going to increase. The glass will actually warm up. Conservation of energy. So most glass, most types of glass, you know what I mean, don't let UV go through them. That's why you don't get a suntan from your windshield, usually.
Hey, I have a question.
Yeah.
If we could see the UV spectrum, would we then see the glass as being opaque?
Yes, exactly. This glass is transparent to visible light. It's opaque to UV light. Yeah, it does not go through it. Good point. Some insects can see in the UV range. There's cool colors on flowers. If you can go out at night and do the black light, that's fun. What's longer than visible? Just longer. You may know already? Past the red. So we got UV, and then we get to violet and blue, because they're higher frequency. Green, yellow, red, and then microwaves would be on this side. Say it again?
Is it radio or is that lower?
Radio is longer. Good. Yeah, that is on this side. It's over here. Infrared is in between the two. Good. See, now you guys are getting the spectrum, getting used to it. IR, infrared. Yeah, they're longer waves. They vibrate more slowly, lower frequency. Again, these all travel at the same speed in air, but they slow down in glass because of these interactions. Well, glass is opaque to IR, infrared. It makes the molecules vibrate. They like to resonate in the infrared range. And so they absorb that energy and don't let it pass. And so it's opaque to IR. And again, it absorbs the IR and causes the glass to heat up because that energy goes into internal energy. So when you see a yellow light come to right here, it's not the same yellow light that comes out. It's a different wave at the same frequency, so it still looks yellow. I find that interesting. But it slows down in between. These are at resonance with the glass. This one is not. Now let me give you those some values I find interesting. The speed of light in a vacuum, we'll just call c. It's 300 million meters per second. In air, close enough. It does interact with the air molecules, and so it does slow down. But it's very, very, very little. So it's essentially still the same. In water, there's more molecules. And it is 75% the speed of light in air or a vacuum. So it slows down a quarter. Glass, like over there, it is about 2/3 the speed of light in a vacuum or air. And one of the extreme ones, diamond, is about 41%. So it slows down by 60%, down to 40%. So there's a lot of interactions in diamond. That's what it's telling us. That time delay to get from the inside to the outside takes longer in diamond. Mirrors. Here's a mirror. Yeah. I know, I need a haircut. I'll look better after I look like you. But I haven't done it yet. Mirrors are kind of special. Are they transparent or opaque? Opaque, yeah. Because the light doesn't go through them. But they're really reflective. That means they don't absorb much of the light at all. So they're not really at resonance. But what's special about most shiny surfaces is they're usually metals. The coating on this is metal. And the electrons in metals are less bound to their atoms. And so when the incoming light makes that electron vibrate at the incoming frequency, that electron doesn't transfer that vibration as well to the atoms it's bound to. And so instead of springing through the material, it just reflects back. And it re-emits that light back at you. We call that reflection. And that's why mirrors are often, metals make good mirrors, because of those loosely bound electrons. So the more reflective something is, you go, oh, I bet that has more loosely bound electrons. You can do that. You got any questions about this so far? That's the key to light. We can do lots of things with it now. It leads us all into color and reflection and refraction and dispersion, lots of things. Lenses, how our glasses work, how our eyeballs work. That's where we're going to head now. So I want to make sure this makes sense to you. Okay, then let's do some shadows. There's two types of shadows. Shadows work because you got something opaque, right? So let's turn on a light source. Hold up an object that's opaque. So it'll absorb some of it. But it's going to block these light rays from reaching the screen. And you get a shadow. And you're like, duh, Adam, we know that. Good, I hope you do. Something to point out, though, is where the light's blocked completely, you get a dark shadow here. And that's called an umbra. Umbra. It's in your book. It's a vocab term. Umbra. It's the really dark spot where no light gets to from that light source. But do you see the fuzzier region around it? That's called a penumbra. Penumbra. Again, another term in your book. And that's because the light from, say, the top of the projector might get blocked by the top of this, but it can hit the bottom, and vice versa. And so you get kind of a fringe area where one side of the light source can reach that part of the screen, but the other side can't. And so it's a partial shadow is what a penumbra means. The umbra is complete darkness, and the penumbra is partial darkness. And it has to do with the type of light source and the relative position of the object. So watch this. If I move closer to the screen, it looks more like an umbra. The penumbra, the fuzzy region's less, isn't it? That's because from the angle, there's less room for the light rays to hit the fuzzy region. Is this making sense? I'll try to draw a picture after this. But if I move closer to the light source, see I get fuzzier and fuzzier? Because it's easier for light to get to one side than the other. And so you see that difference around here. You can change light sources. That one is like normal light sources. This one is what we call a point light source. It comes from a really small LED, a little point. So instead of spreading it all out, it's like coming from one little spot. Picture this one. I'll exaggerate, the light source here. So you got light coming from here and here and here and here and here, and that's why they can overlap on the screen sometimes. But a point light source, they all seem to be coming from the same point. Thus, you get a sharper shadow, less fuzzy region. It still works. If you get closer to the screen, it's even sharper. But you can see I can get a lot closer to the point light source before it even looks fuzzy. There it's starting to look a little fuzzy to me, but not near as much. And that's because it's a point light source. So here's our light source. You can think of it as the sun or a big light bulb. Here's our object. Here's the screen. So let's see. If you take light from here, it can go and just make it. And you got light over here, and here, and here. Oh, that one gets blocked. Oh, that one gets blocked. Oh, that makes it. You get the idea. So you get a shadow. But light from another spot, let's take the extreme, this end, can do the same type of thing. It can hit over there, gets blocked. What if it's heading that way? Oh, that one makes it. You get the idea. So right here is the umbra. Umbra. It's the complete shadow. But here and here, you get the penumbra, where it's a partial shadow, because light from one side's blocked but not the other. Now maybe you can visualize. If you move this closer to the light source, do you see how it can get around more? Makes it fuzzier. Move it this way. Let's do an extreme, like it's way over here. The farther away you get, the light source looks like more like a point light source, and you get less fuzzy region. You could leave it here and just make it a point source. What if the point source was just right here? That's all there was, and you didn't have all this. Then you can see you get this region, and you don't get the fuzziness from something coming from over here. This works in eclipses. Your book discusses it, but you get shadows. Think of your head as the earth, and a light as the sun. You need a ball, right? Picture a ball, or your fist, that'll work. So if that's the sun, and you're the earth, and the moon gets in between you, it casts a shadow on the earth, doesn't it? And at some point you see an umbra. That's where you have a total eclipse. But some people are living or standing in this region, and they see a partial eclipse. And if you're out here, you don't see an eclipse at all. And you can do the other way around too, where if the moon's over here, then the earth is blocking the sunlight and casts a shadow on the moon. And you get a lunar eclipse. So our eyeball allows us to see all this fun stuff. The front is called the cornea. The cornea. And it allows light to refract. Remember what happens when waves change mediums? When light enters your eye from air to your eye, it slows down because there's interactions. And those interactions slow it down, but it also refracts and bends, just like sound waves did when they entered water, let's say. And so they change direction. And that allows us light to focus onto our retina in the back. The lens in our eyeball helps with the focusing, but most of the bending and focusing, about 70 or 80%, come just from light entering your eyeball, and it bends. But then it tries to focus the image on your retina, the back of your eyeball. And that's where our antennas are, if you will, our sensors. They're called rods and cones. We have two types, rods and cones. But think of them as little antennae. The incoming light at a certain frequency land upon them. And if they resonate with them, it's like tuning into your right radio station. And they go, ooh, yeah, and they send a signal to your brain. The cones respond to different frequencies of color. There's three types that we've learned physiologically. One responds to low frequencies like red. One responds to intermediate frequencies like yellow and green. and the other responds to higher frequencies like blue. So your blue cone, if red light hits a blue cone, it doesn't do much. But the red cone will react and send a signal to your brain. The cones respond to color. The rods respond to intensity of light. The brighter something is, the stronger the signal to your brain. And those two types allow us to see everything. They also allow us to have some illusions. I'll pass these out once they're out. Take one, pass it around. We'll use these and then return them. You just, here you go. Grab the box and pass them around. And we'll try something out with you. You guys have any comments or questions? Then I'm going to repeat while you're passing out. At resonance, when the material wants to resonate, light gets absorbed. And where does the energy go? Into the material, internal energy. Some of that will be translational kinetic energy, and it'll warm up. Most objects we know, they reflect rather than transmit. The incoming light vibrates the object's atom and molecules. If they're off resonance, they'll re-emit the light. If it re-emits it so it passes through, we call it transparent. And if they reflect it back, we say it's opaque. And it casts shadows. You can think of selective transmission, we call it. What if you have a colored piece of glass? Let's grab one while you're still passing out. Yeah, here's a green one. We haven't talked about color yet, but what color, what frequency of light do you think passes through this? Green. Yeah, that's why when I hold it up to the light, the white light now looks green. So it's absorbing the other colors. It resonates with those, and they get absorbed. But the green is off resonance and transmits through. It's transparent to green. It's opaque to blue and red, or yellow. Does that make sense? How are we doing? We're getting closer? All right. This can reflect light too. And your homework is find a piece of colored glass, something that's transparent but colored. You can even go color some on you. And I want you to check. You guys see it as green because the light that comes through it's green. What color do you see that reflects off of it? So if I try to see a light and I see the reflection in here, what color is that? Is it green? Or is it the same color? Or do you see a different color? We'll discuss that more next time. Try it out. Okay, with these glasses, they're nothing special. One of them is just a filter to block the light, somewhat. So it allows less light to enter your eye. And so our rods that respond to intensities of light, this one's going to be dependent more on the rods, and this one is using more of the cones. Well, something I find really interesting, one type of optical illusion is the fact that our rods respond more slowly to light, sending a signal to our brain, than the cones do. So the darker the light, it's kind of like you get a delayed signal to your brain. That's a really subtle effect, but you can do some cool things with it. This is called the Pulfric effect. You don't need to memorize it, but Pulfric is a guy's last name that discovered this. And what I'm going to do is stand up here and try to swing this back and forth over this bottle as straight as I can. So to convince yourself, you might take the glasses off at first and see that I am just swinging straight back and forth, right? You agree? Now put your glasses on and tell me if you see the world a little differently. Am I still swinging straight back and forth? Take your glasses off. Sure I am. I'm trying. Put your glasses back on. Which eye is covered? Is it your right eye? take your glasses off and switch them around so that your left eye is covered. You need both eyes. You're just allowing the light to be dimmer in one of them. Whoops. Hit the bottle. What's different now? Hopefully you guys see that it looks like it's going around the bottle slightly in a little oval. Note which direction it seems to be going around to you, and then switch your eyes again. Does it go the other way? Yeah, I think that's cool. So, briefly, what's happening is both of your eyes, you send two signals to your brain. But one eye is referring more to the cones, because you see the color. One's dimmer, it's relying more on the rods. And the dimmed eye is sending a slightly delayed image to your brain. Your brain has to process the two. So, one eye sees the ball here, and your other eye tells your brain, oh, it's right here. How can your brain reconcile that? It's where, well, let's see, if one came from this spot and another came from this spot, your brain says, light from this direction, light from... They must have come from some common point behind, and it adds depth. And the reverse happens when it's coming in the other direction, because they might cross in the front. And so it adds a little three-dimension to it, just because of the two types of sensors in our eye, rods and cones. All right, pull your clickers out, and I got another animation online, and then we'll ask some questions. And yep, of course, the projector just turned off a few minutes ago. All right, this animation is somebody took, well, not animation, they took a video. It's a normal video, so you can watch it without your glasses, but then put your glasses on. And this one, they suggest one eye views through a dark lens and the other does not. In this example, cover your left eye so that your left eye is dim. You'll still use both eyes, but cover your left eye. And so you could have fun yourself going to the amusement park, video something going around. This works with any type of motion. Again, because of this Pulfric effect, that your rods are different than your cones. Without your glasses versus with your glasses, does it look like it's actually going around, adds more depth and 3D to it? Most people think it does. This is fun too if you're riding in your car. Notice I didn't say driving, but riding. And you're looking out the window, you can kind of get an effect that things are moving closer or farther away from you as they move by you. That's kind of freaky. And all you need is just some filter to dim the light coming into one of your eyes. And I got one more, because I think this stuff's cool. I might have to reload that one. Here's just a bunch, with your glasses off. Start with your glasses off on this one. What do you notice? A bunch of random dots moving around. Now put your glasses on. To me, it looks like a cylinder kind of rotating. Switch eyes. And like the pendulum, it should appear like it's going the other direction. You still need both eyes, but one will be dim. Cool, huh? All right. So as you guys pass the box and glasses back down, where'd the box end up? There it is. Yeah, you just throw them back in, and on your way back down, we'll do clickers. Let me pull up the turning point. Get a session ID number for you. Responseware, login. There's the number, lower right. Give you a minute to pull that up, log in before I cover it up. I wish it stayed on top. Okay, let's see if you were listening. Go. Pulling open. I hope this is an easy one. Source of electromagnetic waves is vibrating something or other. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 85% say electrons. All right. Now those of you that chose molecules, it's not the source. They end up vibrating when light's absorbed or something, but that's not what creates the light. There has to be something charged that's vibrating. Electrons are charged. All right, go. What do the atoms in glass have a natural frequency with? All right. And if you missed it, you can run down afterwards. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and okay. Most of you thought visible. Okay. That is not correct. I'll tell you that. All things have a natural frequency. We discussed that with sound. They want to vibrate at a certain frequency. Smaller things generally have a higher natural frequency, and bigger things a lower, like a small bell and a big bell. Materials do too. Glass, for example. The atoms in glass naturally want to vibrate at some frequency. That's its natural frequency. If the driving frequency, sound or incoming light, match that, then we get resonance. And so for one of these types of light, it resonates with the natural frequency of glass, which will make it resonate and wiggle around a lot. And where will that energy go? Into internal energy, including heat. Thus, they will not make it through. Ones that are off resonance might reflect or transmit. They still make it wiggle, but not as much. Like the tuning fork, when it was off resonance, it still wiggles and re-emits a wave, whether reflecting or transmitting. But if it's at resonance, you get more interactions. It makes those atoms vibrate more, and that energy gets dissipated from the wave and goes into the material. So why don't you revote, if that makes more sense. See if you can remember which one of those is at resonance. Polling's open. If you forget, ask your neighbor. I know it's dark, but the picture's on the board. That will help. There were two things on the board there that got absorbed into glass. One caused the electrons to resonate. One caused the molecules to resonate. You can have different types of resonance, and both can make it opaque to that. The electrons are 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's correct. Majority ultraviolet. Ultraviolet is the driving its driving frequency matches the resonant frequency of electrons in glass. Infrared makes the molecules resonate. Both get absorbed and are opaque to those. Visible, those off resonance, and it allows visible light to go through it. Let's do... is it this one? Yeah. Okay, pulling open. Slowing of light in transparent materials has to do with what? It's like the cause of light slowing down as it goes through it. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Bless you. It is A. The time it takes to absorb and re-emit, and absorb and re-emit, and absorb and re-emit, and absorb and re-emit, and get through. The more interactions there are, the longer the time delay, the more it slows down. All frequencies will have that same effect. It still has to absorb and re-emit. It's just whether it makes it resonate or not is whether it comes out at all. But it still makes it wiggle. Any last minute questions? All right, we'll do some more color fun on Wednesday. Have a good day.